Hello everyone, we continue our series about old programming languages, and today we'll talk about Borland Pascal and Free Pascal, very cool programming languages from the old times. This episode is a little bit longer than the first one, so make yourself some tea, some snacks, and enjoy. Borland Pascal. Here we have it. So it's not Borland Pascal, it's Turbo Pascal, but it's basically the same thing. We have two versions, Turbo Pascal and Borland Pascal. The difference was not that important. I just managed to have Turbo Pascal here. It's kind of lightweight version of Borland Pascal, I believe. Yeah. So very classical, let's say, programming system. So it was, you see copyright from 1983. But it's not this version. I believe the first version of Turbo Pascal was in 83, but this version is like version 7, introduced in year 92, and used by me from 97, 96 maybe, and up to 2000, 2001, something like this. Then we moved to Free Pascal because of reasons I will tell you a little bit later. So that's the idea of the Borland Pascal. Again, if you watched previous video about Quick Basic, you maybe have some flashbacks because it looks very, very similar to idea of Quick Basic. Yeah. Again, we have this text window. You can write anything here, and here you program in your runner. Yeah. Again, so you can compare. Let me show you again. So this is the idea of the Quick Basic. And this is the idea of the Borland Pascal, yeah? So very similar, but looks better actually, yes? It looks much better because, I think, because of all these colors. So it's much more colorful than Quick Basic, yeah? And that's why it looks much more modern, yeah? And not only colorful in these menus and here in all elements, but also it's colorful in the text itself. So if you write some keyword like begin, it's so you see it. So it is in white, yes, not in yellow. So if you write something not a keyword, it will be yellow, and if you write a keyword, it will be white, and it make program much more readable. We will see it later. What's another cool thing about this idea, which I kind of adore, is that this text window is actually window. You can move it. Yeah, like in Windows. And imagine that it's not Windows, it's MS-DOS. It's a very old programming system. You have no Windows here. So they need to implement whole this window manager by themselves. So interface designers of that time were kind of crazy for this, yeah. And you do it because you can open multiple windows. So you can create new one, and now you have two windows. You have one and you have two. You can switch between them. You can tile, just move them, yes, horizontally, or you can adjust them as you wish. You can put one here, and okay, not very careful, nice, something like this, yeah. And it's quite useful when you have multiple files to work on. So if you have multiple file project, you need to work on multiple files at the same time. Very cool, very cool. I didn't use that much that time because in competitive programming you don't normally, sometimes you have two files, like your program and the input file, yeah. But again, not that useful for competitive programming, but still cool, right? So Borland Pascal. So what we have. So if you know nothing about Pascal, very simple programming language. Let's write hello world like we usually do. So the program is between keywords begin and end. So between them I have my program. And the simple, so hello world, like write down hello world. Yeah. Okay, if you wanna make clear the screen, so it's easier to read, there is a special command called clear screen. Like this, and to use it you need to using uses, yes, C like this, yeah. So that's a library which have this function which clear the screen. So let's try to run it. Okay, let's solve it. Something like this, yeah. Let's run it. Now we can watch the screen. Ta-da! So that's hello world in Borland Pascal. Yeah. Let's introduce some variables. Let's say you have n integer. Yeah. So every variable should be introduced here before the actual program. It's not very fun when you have tons of variables, but that's the programming language we have. Okay, so to assign value to variable, we have special. This is not equal, like in almost every language. Yes, it's like this. Yeah. So that's how you assign value to variable. Yeah. And yes, and you use single equal sign for comparison. So when you compare elements, yeah, so you have this. No, let's say print. Okay, right. Yeah. That looks fine. Good. Yes. Let's read something. Let's create a plus b like we did with basic. Let's do it really quick. Okay, read a plus b. That's it. That's the whole a plus b program. Now, how we can the cool thing about Pascal, actually, the input library is very cool. So you can input these numbers anyhow. So I can read in one line. It can be 4 or 5. You see. Or I can put them in several lines. So you see, so this read function works whatever delimiter you put between these. So it just skips all the white space basically and waits until it has some numbers. So you can put several white spaces here. Actually. So you can put 3, then 2, then 7, and then it still will read them. Yeah. Very cool, so you don't need to think about how these numbers are located in the input. Nice. So again, let's have some loops. So let's get some Fibonacci numbers. Let's say n equals 10. Okay, then we don't need n. Let's say for I from 1 to 10, do begin end like this. So that's how you make loops. So this begin end block is something like works like these brackets in C++ or Java. Yeah. So they just mark the start and end of the block, and so I usually put them like this. So imagine like this is start of the block, this is end of the block. Just not the single character, but the whole word to use to it. Okay, okay, let's do simple. Okay, we have C. Okay, we'll start again from A equals to. Okay, let's do that like this. B equals 0, and here I will say C equals A plus B. A equals B equals B, B equals C, print C. Yeah, like this. Okay, don't. Okay, I need to introduce these variables also. It's impossible to introduce variable here, like in C++. Again, in old C language, it was kind of the same actually. So it's not that different from any old language. It's just different in modern language. Okay, so here we have Fibonacci numbers. Let's actually check what is the maximal size of the number again. Let's say n equals 1, and here multiply it. Look. Okay, so can we go do 30? Okay, we can you see, so here we have integer overflows, you see. That's because we have 16-bit integers. Yeah? Same as we did in the quick basic. Again, it's something similar for all languages. So we have very small default integer size. If you want to have longer integer, there's special type called long int. Yep, like this. And it actually is, I believe, 32-bit. Yes, it's 32-bit integer, like your normal integer, which you have in any modern language. Next step, arrays. So how we use arrays in this programming language? No, we introduce them like this. We have a array, and we need to set the boundaries for this array. So we set of indices we will use for this array, and indices will, let's say, from 1 to 100. I know. Of something, and here the type of the element of integer. And here we do something. Okay, let's do Fibonacci numbers once again. Let's say a1 equals 1, a2 equals 2. Look. And for every value next, okay, let's do 30. Okay. Okay. We will say I forgot how to use this ID. Let's say AI equals AI minus 1 plus AI minus 2. Okay, let's write all of them here. You can do it without begin end actually, if you like. Like this. Yeah. Okay. One. Okay, that's a lot. That's too much. Let's introduce const equals 10, and here we have equals because it's const. Yeah, point to n to n to n. Oh. Okay, well, why I started Fibonacci numbers from 1 to 1, I don't know. Okay. Okay, now that's more like, okay. So that's how we fill the array of Fibonacci numbers. Again, cool thing actually is this. This thing I like very much. So what we can do here, we can set up the range of the indices we will use. And here I use range from 1 to n because I want this to go. You can do it from 0. If you want to apply element 0, you can do it from 0. What's cool thing, you can do it like it's from minus n to n. So you can introduce even negative indices. And it will just work. So you can here you can do it like from minus n to n and do something like this, like equals I, something like that, and it will just work. Cool, right? Yeah. So negative indices, if you need them, that's okay. Yeah. That's something I actually miss a lot in modern programming languages. For example, in some dynamic programming, sometimes you need indices from -1 or from -2. So it's just logical to make it. So you make so what you do in C++, you shift everything like 2 positions and just remember that your indices are shifted. Or sometimes you actually need indices from -n to n. Like you move something and you in your dynamic programming you remember like the current shift from the middle value, yes, and this shift is from -n to n. You know, problems like this, yeah. So in problems like this, it would be very cool to have indices really from -n to n, yeah. So you don't need to manually shift the whole array and positions and adjust all the indices and stuff. Really cool. So that's how arrays work in it. Another cool feature actually that you can make multi-dimensional arrays. So you can do it like this. So we have 1, 2, 10, 1, 2, 10, like this. Yeah. So it's like two-dimensional array. It has two indices. And you just do it like this. So to access these elements, you just do like a, like, I don't know, 3, 4, 5 equals 10, something like this. Equals, yeah. Very nice. So that's again, in modern language you need to do it like this. Yes. Here you can do both. So these two lines actually do the same thing. I always did it like this because I think it looks much more cool than this. But if you prefer this, you can also do it like this. So that's arrays in Pascal. What about strings? So let's try to do some strings here. Strings are very simple. You just say string. Strings are actually in this language cannot be very long. Yeah. Okay. So let's try to do it. Oh, like this. Okay, let's put something silly here. So you can do it like this, and then just right. Let's remove everything. Yep. Yep. Indices in the string are labeled from left to right from 1. So you do it like this. Okay, okay, let's see. Again, I need to introduce all the variables. Okay, ni integer. Let's see, n equals len, like this, right? Yes. For I from 1 to n, do as like this, like with like the arrays. Yeah. So looks fine. Yeah. So that's how you take individual characters of the string. You just like you do it in any modern language. You just indices up from 1. Don't forget about this. One strange thing about this programming language is that strings are always kind of short. So again, let's try to add more characters. Let's do it like this. Let's start from empty string and try to add like 1000 characters. Can we do it like this? Like good. Huh? So you see, we added like 1000 characters here, 1000 characters A to the string S, but the resulting length of the string S is 255 characters. Yeah, that's because all the strings in Borland Pascal are limited to size 255. That's just how they stored in the memory. So they have 1 byte which stores the length of the string, and then 255 bytes to store the string itself. Not very modern way to do it, but again, that's how they did it. So again, the strings were not supposed to be used for some data analysis, stuff like this. You're not supposed to analyze DNAs and stuff like this. You don't need long strings. You mostly need them for some interfaces and stuff like this. So short strings are practically much more useful. But again, in modern competitive programming, you often need very long strings. Like they give you in the input string of size like 100,000 elements and so on. So But for all times it was okay-ish. Yeah. What else? Let's try to implement, for example, last time we implemented EMP. Let's implement Z algorithm. So array. Let's say of integer. Yeah. Let's do something like this. We have so I will just hard code the string here. Say equal length of yes. Okay, I need to remember all indices from 1. It kind of changes the algorithm, so need to be careful here. Okay, so what is let's implement n square algorithm first. So what we do, we start from 2 to n. Oh, well, let's say k equals 0, while string in position I plus k equals string in position 1 plus k. First, I have 1 indices here. Okay, do k equals k plus 1. You can do it like this actually. Inc of k. It just does k plus 1. It's basically k plus plus. Yeah. Let's say zi equals k. So it's n square algorithm. Okay. Let's do it like this. To right. Z of I and space. Like this. Okay, we don't need this anymore. We don't need this anymore. What else do we need? K. Yep. Okay, let's run. Okay, let's run this. Zero 1, 0 3, 0 1 looks fine. So now what we will do, we will improve it to have linear complexity. Yeah. To do this, we need to remember some left value and some right value. Yeah. So L equals let's start with L equals 0, R equals 0. Now here, if L is not 0, that's how you say not equals. And begin. So if L is not 0, then we need to update K. Yes, so here K equals minimum of what? Of R minus I and what? And Z. So I start from L, my composition is I. Okay, and everything Y index, 1 indexed. Yes, so I have I minus L is my 0 index. Yes, it's plus 1. It looked very strange. If n is maximum of this and 0 actually. You don't have minimums and maximums in this language. Okay. So let's so how function function minimum of a and b integer given and minimum equals so if a is less than b, then do you have return? I don't remember. No. Then okay, minimum equals a, else minimum equals b. Okay, before else you don't put semicolon. Okay, and you need maximum. Okay, we can do it. Okay, I don't have insert in this program. So copy, control, insert. This simple Mac keyboard don't have insert. Okay, I don't have maximum. So if it's greater than maximum, like this. Yeah. Okay, finally, here we need to update left and right. So we say if Li plus z of I is greater than R, then we need to update current block. Yes, so we say IL equals I and R equals I plus zi, like this. Yeah, I think it's this. Wait, hey, hope I didn't make any mistakes here. Let's put something. So. Okay, you will tell me in the comments if I made any mistakes here. Okay, 0, 0, 1, 5, B, 5 looks fine, I guess. 0, 0, 1, 1, 4, yeah. Looks okay. Okay. If I made any mistake, it's that made on purpose, so you can find it and write it in the comments. So again, so pretty programmable language, yes. So again, we don't have minimum and maximum for some reason, but apart from this, nice language, yeah. Again, one indices you need to get used to one indexes for everything. If you move from C++ or any other language which uses zero, which any modern language uses indices from 0. So you need to get used to have indices starting from 1, or you can adjust everything, just make -1 to everything. But apart from this, nice programming language. Just remember the really cool thing about Borland Pascal. So there is nothing basically algorithmical in the standard library. There is no minimum maximum, and there's definitely no sorting algorithm. And the sorting algorithm is something you use a lot, yeah? So when you need to sort array, you need to implement your own sorting. So let's try to do it. Read n for I from 1 to n to read ai. Now, you need to sort the array, yes? And you can implement your own sorting. But again, any sorting which works in n log n time is not that easy to implement. So you need to spend some time implementing your own sorting algorithm. But you can actually steal it. You can steal it. So you can go open file. It's called qsort. And here it is qsort demo. So you can go here and just take this algorithm and copy it and go to your program and then paste it here. Ta-da! You have sorting algorithm. Nice. So again, you need to adjust it sometimes to your needs. So this sorting algorithm takes like this. So it luckily it does exactly what we need. So it takes array A of integers and sort them. Yeah. So let's just use it. So you call it by calling sort. You give it left and right indices of your segment. I believe they are inclusive. Yes, they are inclusive. So I sort from 1 to n. And then just output them. Ta-da! That's how you sort when you need to sort. Let's run it. So yeah, some 6 elements. 6. Oh. So you see they're sorted. What sorting do we have here? We have a quick sort. We have a quick sort with pivot element as the middle here. Like this. So they always pick the middle element. That's not ideal. So some arrays actually sorted in n square time. So if you don't know it, try to find out which array is sorted in square time if you pick middle element like this. But luckily that time it was not that popular. So So judges didn't try to break your program if you use wrong sorting algorithm. So it was okay-ish for almost any problem that period. I would use this sorting and it will work just fine. It kind of looks even strange. So this integer is from capital C, this sorting from capital C. So this div is in capitals. Div is just divide, so it's divide in integers called div in this language. Sometimes you have spaces here, you don't have spaces. I don't know. So okay, so just look of this sorting algorithm is very nostalgic actually. So in every old program I used this sorting. I wanted to show you some real examples of the Pascal code from programming competitions, and what I found is the archive of All Russian Olympiad 2001. It is the first All Russian Olympiad I ever participated, so we will see how my code looked 25 years ago. Yeah, so I solved two problems in this Olympiad, so let's discuss both of them. The first problem is called Olympiad, and the problem looks like this. We have some number of people, and they need to go inside the building, so they are participants of the Olympiad and they need to come inside. But they only have 2 badges. Yes, you see these red things. So they have 2 badges, but they all need to come inside. Yeah. So they decided to do it in the following way. They pick some 2 people, give them 2 badges, and these 2 persons come inside. Now, one of them take both badges and take them outside. Yeah. Now we have one person inside and both badges are outside. Now again, we take any 2 persons. We may take the same person, we may take some other 2 persons, it doesn't matter. So some 2 persons take 2 badges and again they come inside. Yeah. Now we have 3 people inside and 2 badges. So one of these 3 people, it may be one of these 2 people or the one which we put before. So one of these people take again both badges and come outside. And again, now we have 2 people inside, 2 people outside, both badges outside. So we take these 2 badges and the last 2 persons come inside. That's it. Now everybody is inside and everybody's happy. Yeah, that's what we want to do. Now, what we optimize? We optimize the total time we spent during this procedure. So how the time is calculated? Time is calculated like this. So every person has some value assigned to it. So let's take some values. Let's do it in blue. I don't know, something like 3, 2, 5, and 4. So this value indicates how long this person takes to move through the security in both directions. Yeah. So when we have now how the total time is calculated? When 2 persons need to pass the security, like for example these 2, they pass through security. The time they spend equal to maximum of these 2 times, because the fastest one need to wait for the slowest one. Yeah. So the total time we spend moving 2 people through security equal to 5. So let's write something here. Let's say time equals 5. Yeah. Now one of them need to go out. So let's take for example this fastest one. And he goes inside. Okay, again, when he moves outside, he needs to spend 4 units of time, so that time will be plus 4. Now again, we pick some 2 people. Okay, let's say it's 4 and this 3, for example. Yeah. So they together, for example, they come inside. Yeah. Now we spend 4 units of time. Let's say plus 4. Now one of them comes outside. Which one? Let's put this fastest one, for example. This one. It takes 3 units of time. And finally, these 2 people come inside. And it takes another 3 units of time. So that's total time we spent during this process. And we want to minimize this time. Yeah. So the question is to move the people in such order so the total time we spend moving these people back and forth is minimal possible. That's the problem. So I prepared this problem in Codeforces. So here you can read the full problem statement. almost exactly as it was in the original Olympiad 25 years ago. So we have some artifacts of old times like this time, for example. So back then, in almost every contest, in both in ICPC contest, in IOIs contest in Russia, we use this style of input-output files. Input file was called something in and output something out. That's mostly technical part because how your solutions were tested that time. But again, I think it's cool detail. So I kept it for the solution, so you feel how the problem looked that time. Overall, the problem looked kind of similar to what you have now, so nothing actually changed that much during this 25 year. So here you have problem statement, here you have input-output format, some examples here. What you may see, version the constraints are pretty small. So we have at most 1,000 elements in this array. And elements of this array, so these times, are pretty small. That's mostly because back in the days that was not that important that you have that optimal solution, especially for this problem. So for this problem, it's the main thing is to find the idea of the correct solution, to find how this optimal solution look like. But the time complexity wasn't that big deal that time. So that's it. So that's problem statement. I will post the link in the description, so if you want, you can pause the video here and go solve the problem. Problem is actually pretty cool. So if you want, you can stop here, go and solve the problem, then come back and I will tell you the solution. So the solution for the problem is actually pretty simple. So let's sort all the people by the time they need to spend passing the security and look at the slowest person. There are only two interesting ways how can we put this slowest person inside. The first way looks like this. We take the slow person and take the fastest possible person. Yeah. Give them two badges. They come inside. Then we give both badges to the fastest possible person and they come outside. Like this. Yeah. The time we spent in this operation actually equals let's say T1 equals time of the slowest person, because then they both come inside. The time equal to the slowest person, because it's slowest, yes. And then this fastest person come outside. So we have plus T1. Okay. So that's the first operation. We can put... So that's the first operation. We can take the slowest person, fastest person, they come inside, then fastest person come outside. Yeah, so that's the first way we can act. The second way is more interesting. So you can notice that when we come inside, so when the slowest person come inside, the person who is with him is actually not counted in the result, because we count only maximum of these two. So we can take the slowest person and take the second slowest person, yeah, give them two badges and make them come inside. Yeah, so it only takes T2 equals Tn. Yeah, so this time for the second person is hidden. See, but now we have a problem. We need to take these badges outside. To do this, we need to take some fast person who is already inside and ask him to take both the badges outside. So we need to take this person 2, for example, here, give him both the badges and ask him to go outside. It will take another T1. But the problem here that to do this, we need to make this person 1 go inside before everything happens. Yeah. So before it happens, we need somehow kind of implant this first person inside the building. Yes. So how can we do it? So the fastest way, how can we get this first person inside the building, is like this. We take first person and the second person. Yeah. They together come inside. Then the second person take both the badges and comes outside. Okay. Now we have person 1 implanted inside the building. Okay. So this operation costs you plus T2 when they both come inside, and plus another T1 to come outside. So this operation costs you time T2 for both of them to come inside, and plus another T2 for person to come outside. You see? So now we have two options how we can act. We can put inside one person n in this time, or we can put two highest persons inside in this time. And just now we just need to check which way is actually more optimal. And now there are multiple ways to do it actually. So you can do it using dynamic programming. Yeah. So every time you pick one of these ways, and for every prefix you know the optimal way. But you actually can do it using greedy algorithm. So you can prove it by yourself. You can actually take the greedy approach. So you look at two slowest persons, and you pick one of these two approaches. So if you do it like this, you spend this time complexity, and if you take two slowest person and put them one by one, then you will spend Tn plus T1 to put the first one, and plus Tn minus 1 and plus another T1 to put the second one. Yeah, and you just compare these two values and check which one is faster, and that's your solution. Okay, let's read my solution. Again, this is my real solution from the Olympiad, which happened 25 years ago. So that's how I programmed 25 years ago. So here are some compiler parameters. Here are some variables. I have two arrays A and B, not sure why. Again, array C of records. Records basically a struct. So I have some structure of 3 integers. Not sure why. So here are my temporary variables. Back in the time, I used temporary variables named f1, f2, and 3 instead of like I, j, k like I do now. Again, I also use something. So usually named variables are some important ones, but like temporary variables I use in loops and stuff like this are called like this because I'm not very creative, and it was easier for me to remember them by numbers, not by names. Okay, so we have here minimum and maximum just implemented. Sorting, again, it's sorting copied from the standard sorting from it. I just modified it here because I need to sort both arrays at the same time, you see. So what we have here, okay, this reading, okay, that's the main loop. So let's read it. Okay, so what's happening here? So we make iterations, n minus 2 divided by 2. So it's number of iterations when we pick 2 elements. So I stop when I have at most 3 elements. So last three items need to be processed differently. Yeah, okay, makes sense. Okay, so that's okay. That's the index because I sort them in increasing order. So that's the index of 2 last elements. Yeah, so index of the last element, index of the elements next to the last. Okay, so these are 2 times. So this is time of the first approach, time of the second approach. Yeah. Okay, it's 2 plus. Yes, this. Okay, they differently here. So that's time of the first approach. This time of the second approach. Yeah. Okay, L. What is L? It's for copying the result. So okay, so this array C is to store the result. Okay, so if one approach is better, I use this approach. So I store these two operations in the result. One L plus 1. Okay, one increment is here, one increment is here. Okay, why not? And increase time by this. And if not, I use another command. So I use this operation and this operation. Okay, so that's the whole code. Okay, this is quite readable actually, despite the fact I don't use spaces anywhere. It's much more readable than I expected actually. And this naming style is awful, yes, but not that awful. For that simple program, it's okay. Now now I deal with the last element. So if I have odd number of elements, I have one person left who is not processed. So I copy him. And in the end, I just believe, yeah, and I just put 2 last persons inside because they are only person 1 and person 2 are different. I use them in the end. I just move them inside in the last operation. So that's it. So that's my code. Not that bad that I expected actually. Yeah. So again, that's how we solve problems 25 years ago. I'm actually quite proud of myself. Yeah. It's nice code. Yeah. So let's look at the second problem. The second problem is called hopscotch. So what's happening here? We have this grid 3 by n. So this number of rows is always equal to 3. It's important. And we move from the left part to the right part, visiting every cell exactly once. So we start here. Let's say, so let's say you start in some cell here. We can go like here, 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 and something like this. So we're finishing in the last column. Yeah, visiting every cell exactly once. So what we optimize? Every time we jump, we double the current score and increase it by the number in our current cell. Yeah. So every time we have some current score, we multiply it by 2 and add the digit in this current cell. Digits are only zeros and ones. Okay, so if you already figured it out, the score is calculated as binary number, which you read when you follow this path. Yeah, it's not written in the problem statement. I just give you some hints about this problem. So score for this, for example, path will be equal to 1, 1, 0, 1, 0, 0, again 1, 0, 0, then 1, 0, 1, 0, 1. I follow this path, then this part, yes, 1, 1, 1, 0. So that's my current score in binary. Yeah, so this score needs to be maximized. So that's the full problem. So you need to find the path from the left column to the right column, visiting every cell exactly once, so that the number you read is maximal possible. Again, I also put this problem on code forces, so here is the problem statement. Interesting details, for example, here is n is very small, like 80. Again, it's actually not that important for this problem. You will see that the solution actually works for much larger constraints, but again, it's old times. They decided that 80 is enough for some reasons. Actually, some reasons I will explain you why it's 80. What else you can read? It's actually, I actually tell you something. I simplified the problem statement for you here. So this constraint is also important. So you don't need to visit all the cells exactly once. You need to visit them at most once. So and if there are several ways to do it, you can do it in minimal number of jumps. So you need to minimize number of cells you visit. It's actually not that important. Usually you kind of want to visit the whole board because, again, every time you jump, you multiply your score by 2. So it kind of makes sense to make maximal number of jumps. But there is one special case when you actually need to minimize number of jumps. Okay, can you find this special case? I didn't find it during contest, so I didn't solve this problem for the full score, you will see. But again, write in the comments so if you find this special case. So that's it, that's the problem. Let's look at my solution. So let's see how the path may look like. So if we have this grid 3 by n, and we need to visit all the cells, so the path will always look something like this. So I will start in some element here, then I go to the right. Then, because I need to visit these cells, I need to go down, left, again, something like this. Yeah. Then I need to go, then I can go anywhere to the right. Let's go here. At some point, I move up. Yeah. And now when I move up, I need to go left to visit all these cells. So I go here, here. Okay. And again, I go right to some position. Let's go to this position. And again, I need to go left. I need to visit this cell. So when I go down, I eventually need to go left and here, yeah, and so on. So sometimes you can go straight up like this, or something like this. Up. So that's it. Can you stop here? Up, 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 up. So your path eventually will look something like this. Let's make it a little bit more bold. Can we do it a little bit more bold? Up, up, up like this. Now, your path is always split into like S-shaped blocks. So first I have this block. Up, 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 up. You see when I do this. Then I have this block here. when I do something like this. Yeah, and then again I have this block when I do something like this, and then this block. So this is a little bit strange, but it's just S block of size 1. Yeah, so I have very narrow block, and then again this block. So basically, a problem looks like this. You need to split your whole grid into these blocks, maximizing the total value. Yeah, but it's easy to see that the result will look like this. I have result for the first block, then the result for the second block, result for the third block, and so on. Yeah, so this is my final answer. So to do it this, you can maximize each prefix independently. So you can apply dynamic programming now. Yeah. So if you find the maximal result for each prefix you can get, you can just add these blocks one by one, achieving the maximum prefix. Yeah. Okay. Starting from this, it's easy actually to apply the dynamic programming. The only problem here is that the numbers we're looking for are quite large. Yeah. So if we have n up to 80, yeah, so the length of this number will be will be up to 240, right? So numbers, we need to work with numbers up to 2 power 2040. Yeah, so it's hard to do it using regular numbers. Yeah, so they don't fit in any integer type, especially 25 years ago. Yeah, so what we will do instead of manipulating with integers, we will manipulate with strings. We will compare numbers as strings. Yeah, and it's easy to do. You don't need any special thing. You can just manipulate with binary strings. You don't even need to optimize here. So you can operate with binary strings as with numbers. Yeah, and just extend them and compare them like you usually do. That's it. So what we'll do dynamic programming over prefixes. Every time for every prefix, I will try to add this as shape. Yeah, and calculate the maximal possible result. And I calculate this maximal possible result in a string because it can be large. And I compare these strings like the integers. Yeah. So let's look at my solution. Okay, so here is my solution again 25 years ago, remember. Yeah. So first of all, it's much more complicated than I expected. So what we have here, so we have this strange array. Array from 0 to 1 with characters 0 and 1. Okay, I believe I used this array to transfer from integers to characters. Not sure if it's the easiest way, but we'll see. So now I have, so this is my dynamic programming array. I believe this. Okay, I have B and P. Not sure I have two of them. I believe I store the path in the same array. So array B is array of dynamic programming, and array P is the array of the results. Yeah, so I don't have these back pointers. I just store the paths in the dynamic program because I can. Yeah. So it's 0 by 1 because I need to remember which shape I have. Yes. So I have two different shapes of the blocks. So for both shapes, and so here the size of my array. Again, that's cool. I have some arrays I have from 0. You see, some arrays I have from 1 because I can. This thing I noticed is actually looks nice. Yeah. So you can actually make array of some strange integer type. So you can introduce your own integer type like this. So it's integer type that only have zeros and ones. Nice. I didn't remember we can do it in Pascal. What else? No, it's not that important. C. What is C? I'm not sure what is C. Why I need another array? Not sure. We will see. Okay. So this. Okay, this is helper function which build these blocks. Yeah. So it builds blocks from I to J, yeah, so from column I to column J inclusive, like we see here, and depending on this Q, it's either one shape or another shape, yeah, so if Q equals 0, we have this shape, we go left to right, right to left, left to right, and if it's vice versa, we do in other direction. No, we always go left to right, right to left, left to right, but here we use rows 1, 2, and 3, and here we use rows 3, 2, and 1, you see? Okay, and here is where I use this strange array because I need to go from integers to characters. Okay, why not? It works. No, I passed the tests. That's the most important part. Okay, another helper function which actually builds the path. So I have two functions. One function returns the number I will get if I follow this path, and another function actually writes you the path you need. Yeah. So the path looks like this: some number r, then down, left, down, because you need to output the result again. Okay, so we have these two helper function, and here I believe we just have the dynamic programming. Yes. Okay, so what is about this p string? So this p string, instead of you having just array of strings, I have array of pointers to strings. That's because in Borland Pascal you're not allowed to have that large array of strings. Again, if you just make string here, okay, we can try. Can we just compile it? Oop. Yeah, it will say too many variables. So too many variables means you're just not allowed to spend so much memory in normal Borland Pascal. But you can do it if you use some heap space. So what you do? You make array of pointers, and then here you reserve space in the heap, like this. Oh yeah, here. So here I just reserve space in the heap, and that you're allowed to do. Don't ask me why, it's all language. Here, now, I just fill it with, okay, this I start dynamic programming, and here I do my dynamic programming. Okay, dynamic programming is actually not that difficult, you see. So I follow it. Okay, I put some empty string is because I maximize empty string is small, so it's basically making minus infinity. Yes. So here I try to add this prefix to this path. Okay, if it is more than my current result, I update my current result. Okay, that's strange code. Okay, I take this path and then add one of these constructions, depending on what? Because, okay, because I don't have this extra step, I need to do this extra step R, you see? From the previous block to my block, I need to jump one position to the right. I don't need to do it if I'm standing in the first block. So first block I just start, every next block I would just, okay, now I would just always do R and then remove it in the end. It would be much more simple. Okay, and here finally, yeah, here I have two options. I will finish either in this cell or in this cell. So I take maximum of these two options and output the result. Nice. Actually, pretty simple code. I'm surprised it's that simple. So I expect it to be much more difficult that time. Again, problem is not that difficult. If you look at it from modern perspective, it probably would be like the first problem of all rational input. But for again 25 years ago, it was considered a pretty complicated dynamic programming problems. Again, dynamic programming was not that normal back in the day, so it was considered some difficult topic. I remember it was one of the first problems I ever solved in a real contest using dynamic programming. So yeah, good for me. Again, see, I'm actually surprised how good I programmed 25 years ago. Nice. So that's the second problem. So because Borland stopped supporting Borland Pascal anymore, and because of these problems with memory, we have to move to some another system, and the system was Free Pascal. Free Pascal was just created back in the days, so it was created, I believe, in it's just year 98 to 2001, I believe. So we started using in the year 2001, I believe, and so this was one of the first non-beta versions of the Free Pascal. So it's version 1.6. I believe it's like almost, so I can almost not the same. So it's version from year 2002. So I believe we used even earlier versions of the Free Pascal when it was still in beta. So very nice programming system. Again, if you take some look at some program, so that's the idea. It looks basically the same like in Borland Pascal. You can do all the same things like begin and all the same things. All the key mapping is the same. So F9 is okay, but you need to test. So F9 is to compile the code. You can to run it. You to make the flash. You can run for Control F9. Yes. So input. So F3, F2 to save, F3 to open. So all the shortkeys are the same. ID is pretty much the same. You have all the same things with moving windows. So for anybody who used to use Borland Pascal, it was very convenient to move to Free Pascal. Language is basically the same, some minor changes in the language. So if you used to program in Borland Pascal, you can just move to Free Pascal and feel very comfortable. Again, back in the days, it was very raw, so we used some beta versions. It had some problems. I remember sometimes it was crashed for strange reasons. So you just learn not to do some specific things which will lead to crash. So after some time you just learn that if you do this, it will crash. So you just don't do this. I remember the debugger didn't work that well that time, so we just didn't use debugger. That's how I used to debug without debugger. Yeah, I still using these tricks. But the most important part, actually, why it was much better than Borland Pascal, that now you can make a big arrays. So now I can do something like this: a array of let's say million of integer. That's something you can do in Borland Pascal, but now you can use. You can just compile and it compiles perfectly. Yeah. So now you can make a big array, so you can read big amount of data. You can make programs which actually use a lot of memory. That's what's cool. So we used Free Pascal up to year 2002, I believe. I used it in IUI in 2002. While preparing this video, I found some materials from IUI 2002, and here is the programming environment used in IUI 2002, just so you feel the vibe of this age, So here it is. So what we have in IUI 2002. So we have two programming languages. We have Pascal and C++, and we use Free Pascal and GCC. Okay, that makes sense. For the computer here, we use PC with Pentium 4 processor and 256 megabytes RAM. Megabytes, you see. Okay, so you need to fit everything in this amount of RAM. I believe now you can just start Chrome with this amount of memory. Yeah, but back in year 2002, that was okay for the programming competition. And 19-inch CRT. CRT is a monitor. Yeah, so this, this huge monitor with this lamp. Yeah. So that's how we programmed 25 years ago. So for programming languages, we have this is some normal stuff, old stuff, but normal stuff. And for Pascal, yes, we use Pascal version 1.0.6. That's exactly the same version we used in this video. So in this video, we have a very authentic feeling of how it was 25 years ago during the IUI 2002. Also, thanks to Piotr Mitrachuk, we have some photos from IUI 2002. So that's our team. That's me. And that's a computer used at IUI 2002. Now back to the video. Unfortunately, we don't have archives of the IUI submissions, so I can't show you my programs from IUI. It's maybe unfortunate because it would be too embarrassing. I failed miserably during the IUI, but that's okay. So we will not look at my solutions during IUI. Instead, let's solve some modern problem using Free Pascal. So Free Pascal is actually a compiler which is still supported by community. Yeah, so even in Codeforces you can find it here. Yeah, so it's version 3.2. Again, we use version 1.0.6, remember? Yeah, so it's much more sophisticated than the original version, but it's okay for us. It should be back compatible. Yeah, so what we'll try to do, we'll solve a problem, modern problem, using this old language. Let's try. So the problem I chose is called periodic switch. It's a problem for one of the JetBrains youth challenges. Problem looks like this. You have some number of lamps organized in a circle. You start from one of the lamps with number 1. Let's put some number, let's say number 1. So let's say this lamp is number 1. Yeah. So you start from here and you apply the flip operation. So you take this lamp and flip the state. If it's on, you take it, make it off. If it's off, you make it. So this lamp is off. So let's turn it on. Pop. Yeah. Then you jump k positions along this circle. So let's say k, for example, equals, I don't know, 2. Yeah. So we start from here, we jump here, and then we flip state of this lamp. Again, it is now on, so we make it off. Yeah. Now continue from here. So from here we jump to this lamp, and again, this lamp is off, so we make it turn on. And so on. So we continue moving, and the question is following. So now we need to answer the queries. Each query is the following. We make D steps, D jumps, let's see. And we need to answer how many lamps are currently on. So if we make D jumps, we need to say how many lamps turn on. That's it. So we have many queries, but K is the same. That's important. So this number K is the same. We only have different numbers D. So for different numbers D, we need to answer this query. Again, here is the problem statement in Codeforces if you want to solve it. Again, if you want to solve it, stop the video now, go solve it, then come back. I will wait, do it. Okay, so how to solve this problem? So you can notice that if you make n jumps, you will finish in the same lamp which you started, yeah? Because the total distance you travel will be equal to k multiplied by n, yeah? Modulo n will be equal to 0. So you will start in the same, finish in the same node you started, yeah? But the state of the lamps will be different, yeah? So it's not like, so it's cyclic by the lamps you visit, but it's not cyclic by the states you visit, yeah? But you can notice that if you make the same n jumps once again, then you will flip all the lamps even number of times, yeah? So you flip all the lamps even number of times, so states of all the lamps will be the same, yeah? So if you make 2n jumps, the state of all the lamps will keep the same, yeah? So you can, instead of thinking about D, you can think only about remainder of D modulo 2n, yeah? So for every remainder modulo to n, you need to answer how many lamps are turned on, yeah? And we can pre-calculate it. We can just simulate 2n jumps, yeah? Just using brute force, just simulate 2n jumps, and remember how many lamps are turned on for every remainder. And then we will give the query, we will look in our pre-calculation table and give the result from this pre-calculation table. That's it. So let's try to implement it. So I will put this input in a separate window here, just because I can, just to show you how cool is that you can do it in this old IDE. And I will redirect my input to, so my read command reads from this input file, not from keyboard, yeah? So that's how you test back in the days. So you don't redirect input, you redirect it like this. I will remove it before I submit, if I don't forget. Okay, so let's try to solve the problem now. So what we need to do, let's remember, so we need to read the input. So first you read a number of tests. Okay, let's read. Var, let's say t integer. Okay, read number of tests. Now we need to pass all the tests. Okay, for not this language. A from 1 to t do begin and okay. Now we need to okay, process the test. Let's do a function. Can we do function in this language? Let's do solve test. You don't need brackets actually. If you have no parameters, you don't need brackets. Okay, let's say procedure. Procedure is just function which doesn't return anything. Solve test. Do you need brackets here if you don't have parameters? I believe you can. I need yes. Begin end. Does it work? One error. ed pattern not found. Ah, you don't have I. Okay, okay. Let's actually move this here. T and I. So depending on where you put this var, this function may use it or not use it. So if you put this var after the function, I believe if it works like this, yeah, then this function cannot use these global variables, and it makes sense. Let's not use the global variables. Good, it's compiling. So now let's solve the test. So let's solve the test. Oop. Okay, okay. Boom. Let's go. So what we need? We need to read the string. Okay, let's read. Okay, var string. readln s. Okay, I would use readln because I always use readln when I read strings. I also need to read n and k, yes. N and k integer. Let's use long int. Okay, let's do it like this. Type. I still remember how to do it. Int equals long int. Yeah. So it's up. Now everything is long int. Again, long int is just 32 bits. Remember, it's not long. It's just normal int. Okay, so we read, and now we. Okay, and then we need to process the queries. Okay, let's do some pre-processing and then answer the queries. So I will need to store my. Okay, I kind of want to have local array here, but it's complicated. So making array of the variable size. Let's have here. So let's have array of large size. So let's have var. So pre-calculations array will be array of 0 to what is the maximal size here? 10 power 5. Okay, to 10 power 5 of integer. So that will be my pre-calculation array. Okay, so after I filled it, I do it like this. I will read q. I will read q. I didn't read nk. Okay, I read q, and then I read all these queries for e1 to q. Let's say x read x. Okay, it's I x, a lot of them. Not x is d. Yeah, I need to read this value d and write what. Do I need to write them in the same line or not? Doesn't matter, I believe. Okay, let's add the same line. Let's write then the r of d modulo 2n, like this, right? Can I do it like this? I believe so. Do. Yes. Different language. Begin. Okay. Nice. Does it compile? Okay, it gives me some zeros, you see. Okay, so zeros because I have this I didn't write this pre-processing phase. So let's write this pre-processing phase. Okay. So we need to fill this array R somehow. Let's do it. So for I 1 to n, do begin. We need to remember our current position. So let's put it in some C. Okay, C equals 1. Now every time we move to a current position, we say C equals C plus K, and you normally would do it like this. Yeah, but because we have one indexation, so if you go to position n, it will be 0. It's not what you want. Yeah. So what will you do? What can you do in this situation? You can do it like this, for example. You can do -1 and then do +1. That's a cheeky way to do it, actually. Yeah. So what I'm doing here, I move to 0 indexation, do this module operation, and then move back to 1 indexation. Okay, spending that much time solving problem in 0 indexation actually changed my mind. So I don't like indices from 1 anymore. Okay, but that's how you move k positions using 1 indexing. Okay, so now we need to change. So if s c equals 0, then n begin and else begin So if it is 0, we will move it, we will make it equal 1. And if it is 1, we will make it equal 0. Yeah, so we'll flip this value. And now we need to calculate the number of lights which are actually on. So let's find another, let's make another variable s. We already have s. Let's have some variable which don't have, which number, which letter we don't have yet. Let's put some letter, I don't know, T. Okay. I'm not as good as at figuring out the good naming still. Okay, so first we will calculate this number t. T equals 0 for I 1 to n. I will not begin it because I'm curious. Yes. So if si equals 1, then okay, not this language. Then inc t. Inc basically increased by 1, so it's t equals t plus 1. Okay, here, so if I switch 0 to 1, then t must be increased. If I switch it to 0, then t must be decreased. Yeah, and then just put this to the result. So r modulo 2n equals t, like this. Okay, fatal error. Oh, that's okay. Looks fine. Okay, 5. Minus 5 doesn't look great. Why I have minus 5? How can it be minus 5? Ah, I found the problem. Okay. Okay, not s equals. Now we need to change only one character. Again, because it uses the same quotes for both characters and strings, you can, instead of assign one character, you can assign the whole string. Okay, that's not what we want. Okay, let's fix this. Okay, run again. Let's clear the screen actually to make better look. What? Ah, you need to use, okay. Like this. Ah, to put uses in the beginning. Need to remove it before we submit. Okay. Okay, it's much better now. Yes, yeah? So now we have 1 2 3 3 was 0 1 1 3 2. So that's it. So that it works. So let's remove everything which we don't need. Let's remove this, remove this, remove this, up, and submit. Nice, it passed. Again, the time is not that bad. So we have 200 milliseconds for this problem. Again, it's not the hardest problem in the world, but we solved it in a language which is 30 years old. Yeah. Okay, it was cool to remember old days and programming some old programming languages. And in the next video we'll continue, because next video will be about Borland Delphi, another programming system for Pascal, which I used my whole ICPC career. So we started it in 2002 and we finished in 2005. So all these 4 years I used Borland Delphi as my main programming language. And actually I used it a couple of years after that, occasionally in some other contests. So see you next time. We'll talk about Delphi.